Statistics Unit 4, Lesson 3, Two Proportions. In this lesson, we want to find confidence intervals and test hypotheses about a difference in two population proportions. So instead of just having from one population, we might want to compare the proportions in two different populations by looking at their difference pi1 minus pi2. So we're going to have a population 1 with a proportion pi1. We'll take out n1 as a sample and get a sample proportion of p hat 1. And then from population 2, which has a population proportion of pi2, we're going to take out a sample of n2 and get a sample proportion of p hat 2. Our point estimate of pi1 minus pi2 is the difference in the sample proportions. And if n1 p1 hat, so this is the number with and the number without in population 1, and the number with and the number without in population 2, are all of those more than 5, again, bigger than 10 is even better, and both sample sizes are more than 30, then we can use a standard normal approximation. For a confidence interval, that will look like this. You take the sample difference plus or minus the z1 minus alpha over 2, where you're going to take a p hat 1 times a 1 minus p hat 1 over n1 plus a p hat 2 times a 1 minus p hat 2 over n2, and of course take the square root of that for the standard deviation. This is available in two proportion z interval, where you have to put the number with the characteristic and the sample size for both of them, put your confidence level, and then calculate. When you interpret that, you're going to know that the difference is between the lower and the upper, and then we'll use that to interpret. So we'll say that pi1 is from this much. If L is a positive number, you would say it's from that much higher. If it's a negative number, you would end up saying it's from that much lower, and the same on the other end. So you would say pi1 is from this much, and it will be either higher or lower depending on whether that's positive or negative, to this much higher or lower depending on whether this is positive or negative. If you want to test hypotheses, again, there will be one of three different ones that you could have. You have pi1 is equal to pi2, or pi1 is different from pi2, meaning that the difference is either 0 or not 0. Pi1 minus pi2 is equal to 0, or pi1 is bigger than pi2 would be this one. Pi1 is equal to pi2, or pi1 is less than pi2 would be this one. And if the null hypothesis is true, then both of these proportions estimate the same value, so we will have a pooled estimate of, it's the total number width over the total sample size, where n1 p hat 1 is the number width in the first sample, and n2 p hat 2 is the number in the second sample width. So when you combine them, you get the total number width. And then our test statistic, we take the difference in the proportions. We're really subtracting the hypothesized value of 0 there. And then we're going to pool these together. They're both the same thing. So we would have p hat times 1 minus p hat times the quantity 1 over n1 plus 1 over n2. And that will have an approximate standard normal distribution. Use rejection regions are exactly as before, or we can reject as h0 of p value is less than alpha, or for example, the different alternative would be less than the z alpha 2 or bigger than the z1 minus alpha 2 for the test statistic. Time magazine reported the result of a telephone poll of 800 adult Americans. Respondents were asked if the federal tax on cigarettes should be raised to pay for health care reform. Among 605 non-smokers, 351 said the federal tax should be raised for this. Among 195 smokers, only 41 said yes for the tax. At the significance level of 0.05, is there sufficient evidence to conclude that smokers and non-smokers differ significantly with respect to their opinions? So the variable is whether or not the federal tax should be raised to pay for health care reform. The first population is non-smokers, the second one is smokers. These were their sample sizes. The p hat for the first one was 0.58 and the p hat 1 is 0.21. They look different, but we again want to know whether that's a significant difference. We're going to use, the formula uses the pooled one, so we're also going to pool them together, and that together gives me a 0.49. We look at the number with and the number without. The number with is 351. The number without would be 605 minus that 351, or 254. The number with here was 41. The number without is 195 minus that 41. Those numbers are all more than 5. In fact, they're all well more than 10. And the sample sizes are all more than 30, so we can use the standard normal approximation. We want to test whether that difference is equal to 0 or not equal to 0. We could also write that pi1 is equal to pi2 or pi1 is not equal to pi2. Technically, what we're doing is this. It means the same thing. Z is this test statistic, which we've seen. The observed value, if you calculate it, will be 8.9859, and we know from its size that that's an unlikely value. The p-value is approximately 0. Formally, the rejection rules are if z is less than the minus z value or bigger than the positive z value, where again those can come from the inverse normal. And then you would reject H0 if the p-value is less than alpha. Again, that's a very large z value, very small p-value. We would reject H0, and we can conclude that pi 1 is different than pi 2, meaning that there's a difference in the proportions of non-smokers and smokers who believe the federal cigarette tax should be raised to pace for healthcare reform. Now for our confidence interval application, we have males and females who are asked about whether or not they would return a $100 bill mistakenly received by mail to a neighbor. Of the 69 males sampled, 52 said yes. Of the 131 females sampled, 120 said yes. Find and interpret a 95% confidence interval for the difference between the two proportions. The variable is whether or not they would return the $100 bill. For the males, the proportion was 52 out of 69, or 0.753. For the females, it was 120 over 131, or 0.916. The number with and without, the number with 52, the without would be 69 minus that, or 17. The number with 129, the number without 131 minus that, that's 11. Those are all more than 5, and there are even more than 10. The sample sizes are more than 30, so we can use the standard normal approximation. You now take the difference in the proportions, plus or minus z1 minus alpha over 2, and then this estimate of the standard error. Here they're not pooled because we don't know that they're equal. And we would get from a minus 0.2746 to a minus 0.0502. And because these are both negative, that would mean that for the proportion for males, you would conclude that that's from this much less to this much less than, and you would really switch them because they would go the other way now. It would be from this much less to this much less than for females. So we are 95% confident that the proportion of men who would return the $100 is from 5% to 27.4% less than the proportion of women who would return that $100. And just to show you for the confidence interval, it's similar for the test statistic where that comes from. Remember that you go to stat and you go to test. You have the 2 proportion z interval, and then you also have a 2 proportion t-test somewhere else. So this is the 2 proportion interval. For this one, you would put in the numbers. There's 52 with, and then that was a total of n1, which was 69. And then you had the number width for the females, which was 120 out of 131. And we want a 95% confidence interval, so that would be that. Would give me this, which is where these numbers come from. It also calculated those proportions for you. The z-test is similar. Up here we would have selected the different than alternative.